the first problem is to prove the Goodman-Gotzel theorem, which is that the expected characteristic polynomial, the assigned adjacency matrix, is the matching polynomial. So the thing is, I suspect some of you, many of you, might have seen the proof. So I would like to solicit ideas from those who have not seen it, who thought about it now, and want to suggest how to do this. Any volunteers?
I think it's just coefficient-wise.
So you, yeah, so.
Is there anybody who has not seen it? Yes. Oh, great. Great.
Can we get all the permutations or that correspond to computing the determinant?
Yeah.
And if you, so you have to pick both edges, both entries in the matrix corresponding to an edge if you don't want the term to cancel out, because otherwise you have -1 and +1 for each of them.
Yeah. Well, yeah. So would you like to volunteer, or should I?
I think it's one of the theorems that's best proven by staring at it without writing anything.
Try to prove it by picture. You want to come up here, or rather not? So we have this matrix, right? We have x's diagonal, and then we have this minus s. Yeah, so it's a minus. So these are plus minus ones, right? SUV is plus minus 1.
I mean, are you assuming it's a symmetric matrix?
It is symmetric, yeah, they're both minuses.
Okay.
Yeah. Yeah.
In that case, I don't think
You can see, I think it's correct,
Oh,
but I think it's okay.
Okay.
Let's see. So, okay, so what kind of permutation can contribute to this? So let's see what kinds of permutations actually cancel out. Because you had a claim about that, right?
Yeah. So if there is some edge that this permutation only has one of its entries in this matrix, then we're counting so that the product of, so suppose it only contains this one. So the product of everything else, if it's P, then you have 1/2 probability P and 1/2 probability minus P.
Yes. Yeah.
Otherwise, you're counting.
So you must have both.
Yeah, you must have
Yeah.
both, and there's some there's some entries in the diagonal.
Exactly. Yeah. So you have some edges, and you have some entries on the diagonal which are actually the vertices not covered by the matching, right? It must be a matching because it's a permutation which consists of 2 cycles and fixed points. That's the only thing. So let's actually verify this. You were suspicious, but I think it's correct. Yeah, so the contribution, so permutation phi consisting of 2 cycles. The 2 cycles must form a matching. So they correspond to a matching. Not necessarily perfect. And then we have some 1 cycles, which are going to be the entries on the diagonal. Those are the vertices not covered by the matching, right? So this permutation in expectation contributes x to the number of uncovered vertices times the sign of the permutation, which is actually the number of 2 cycles. Each 2 cycle will flip the sign. So -1 to the number of 2's. So I think that's it. Yeah. Thank you. Thank you. The second exercise is the direction of Fell's theorem, which we did not prove, which is that if f and g have a common interlacing, then every convex combination is real rooted. So this is simpler to prove. A little hint, it's simpler to prove when you assume that there are no multiple roots. The multiple roots are slightly annoying. You have to think about what to do with them. But let's solve it first in the case where you don't have multiple roots, and then let's say something about multiple roots. This actually has a nice proof by picture. So somebody wants to suggest.
Don't you have to assume that the highest coefficients have the same sign or something like that?
Oh, correct. So it was in the slides, I think, but yeah, we should assume. Let's assume they're both monic. The leading coefficient is just 1. Yes.
Then they change sign as they should.
Yeah. So you have a solution? Yes. But you will withhold it for now. Somebody from the younger crowd. What we might do. So we have 2 polynomials, they have a common interlacing, and remember the picture, it means that they oscillate in a consistent way. And let's assume for now that they have n distinct roots, each of them.
They change signs.
Yeah. Yeah, they change signs in the same way. Yes.
They have to have
Yes. Yes. So, would you like to? Still young. Do you want to come up to the board? No, you refuse. Okay. Well, okay. So, yeah. So if we assume that they have n simple roots, then indeed it's pretty clean. So let's say, let me actually follow the convention from the slides that we have a blue polynomial, then we have these black separation points on the real line, and we have a red polynomial which oscillates, which crosses the real axis between the black points as it should. Similar to the blue polynomial. Okay, so now when you evaluate these polynomials at the black points, let's also assume that these black points are actually not the roots themselves, that the roots are strictly between them. Then we see that the sign of the blue polynomial and the red polynomial, I believe that's what you mean, alternates in the same fashion. So it's because they were assumed to be both leading coefficient to 1, and in plus infinity direction they have to go to plus infinity. So here it should be plus 1. It should be plus. The sign is plus. Here it's minus. Here it's plus. Here it's minus, and here it's plus. Okay, and now we take a convex combination, right? So if you take a convex combination, the signs still flip in exactly the same fashion. So the signs of ht of x, which is the convex combination, they alternate in the same fashion. So, because of the degree and the number of times it goes up and down, we know that it must actually cross the real axis exactly once between each pair of black points. Because we have a certain degree, and this red and blue polynomial, they have n distinct roots, and so will this averaged polynomial, which is between them. So h dx must cross the real axis n times, just like f and g. All right, so now there's this slightly annoying question of multiple roots. Does somebody have a clean suggestion how to deal with the case of multiple roots? We want to make the same statement. What can happen with multiple roots is that, for example, these black points, we could have several of them might coincide, and then we have these blue and red roots. They could be squeezed together into one point, and you could have a bunch of roots in the same location. So how do you deal with that? We need some simple trick to say that this is okay. Yes?
All the multiple roots have to be common between the two polynomials, it seems.
Well, so it's a little, okay, so for example, you could have a double root of one of the two polynomials, and it could be a triple root of the other one, and the interlacing could still be okay when you think about it. So
You can still factor them out, right?
To make them all.
well, okay, so yeah, so what is your, what is the suggestion?
I mean, what I'd like to do is just factor out enough common roots that we reduce to this case. So even if one of them has a double root and the other has a triple root, perhaps I still factor out.
Okay, so there's a distinction here between shared roots and multiple roots. So they could have shared roots, but also maybe the roots are not shared at all. Maybe a polynomial has double root, so then what happens? Then you have to say something. I guess it's impossible that one polynomial has a double root and the other polynomial doesn't have any root around that area.
Right, so they,
But you have to be careful, and it gets kind of messy. When you start classifying...
Can't we always perturb them? Sort of.
Okay. Yes.
Can we?
Well, if you say so, yeah. Yes, so we could, if you do it carefully, yes.
Right, just
Yes.
push them.
Push them. So you have to push them carefully, yeah. So, yes.
You have to have a right definition, though. Are you sure your definition was correct?
The definition of,
Interlacing in the...
I think so.
Do you assume that the degrees are the same?
Yes.
Yeah, I think. Yeah.
Yes, degrees were assumed to be the same,
Then
yeah.
if f has double root and g and they're interlacing, then g should also have a root at that point, no?
yeah, this is
Yeah, at least that... Huh?
F and G are not interlacing, right?
No, they interlace.
They have a common interlacing. Yeah, that's the difference. Yeah. It's not that F interlaces G, but F and G have a common interlacing. But I think it's still true.
All the black points are always disjoint, right? None of the two black points can be same ever.
They could be. So if you have,
If the two black points are same, then
according to the definition, they could be. Yeah. So the definition, maybe I should tell you what the definition is. So, and I hope it's the correct definition. So the definition, common interlacing. Common interlacing means that alpha k and beta k are both in gamma k, the closed interval, gamma k minus 1 for some n more than
Is that a common relation? And
there is no.
Right. So if some two gammas are equal, then The roots are equal.
then you should have, yes. So if two gammas are equal, then you should have both alpha root and a beta root in there coinciding with that.
But that doesn't say
Yeah,
anything about
but-
double roots. Like you could have one polynomial with
Yeah.
double root, the other with two.
Yeah, it could be a mess because you could have another root of, like one of the polynomials could have a double root, but maybe the f is only single root and g is it's a double root. I still, I would like to come back to your suggestion, which was to tweak it to avoid this situation. And maybe you can classify all these situations. It's certainly possible because the result should be true, but I don't see a very clean way to do it actually. Like a one-shot argument that says how to handle all these possibly coinciding multiple roots.
There is one.
Is there?
You hit it by 1 plus epsilon d to the n.
Aha, so you perturb it. Yes. Yes. So you had, okay, would you like to volunteer on the... Yeah, I think the only clean way, there are different ways to perturb it, but I think the solution is to tweak the polynomials so that they actually have distinct single roots, and then you use a limiting argument.
You need a way to tweak them that preserves convex combinations. So you need to tweak them with a linear operator.
You have to tweak them. Is it? Oh no, I mean you can have a sequence of polynomials that converges to f, converges to g, so the convex combinations will converge. I'm not sure if you have to be particularly careful about that.
Why do you have to do that?
I think it's fine.
It has to be real rooted.
You can think about perturbing the roots, actually.
Okay, maybe I'm thinking of going the other direction. To the other, if you want to do this in the other direction, then you use a linear operator.
Yeah. I think here, I don't know. There might be different ways to perturb them. For me, the easiest way is to think about actually perturbing the roots themselves. You can just push the roots apart a little bit. So
Still, I mean, this definition is kind of ambiguous. So what exactly is alpha sub k?
alpha sub k is the kth largest root. I think that's...
But what if there are 3 of them?
If they're
three of them or 2?
like coinciding roots?
Yes.
Then you can just label them. I mean, this is clear, no? So f has the roots. F has the roots alpha and at most alpha.
We're not concerned with gamma.
So when you say alpha sub k is in that interval, so then some other root.
Okay, so it's a real rooted polynomial, so I can label the roots in an ordered way. And then I say there exist real numbers gamma k such that the kth root of f and also the kth root of g are in this interval. I think it's pretty clear.
So if you assume that the f and g have no common roots, all the gamma is are distinct, right? If you assume f and g has no common root.
These are two different things: common roots and multiple roots.
No, I agree.
Yeah. So you're saying,
If f and g has no common roots,
yeah.
then all the gamma is are distinct, right?
And then it's not feasible.
Well, not.
No. Because otherwise, by definition, if gamma I equals to gamma I minus 1, alpha I has to be exactly equal to beta, right?
I mean, you're saying it's possible to choose the gammas so that they are distinct.
I'm saying if you assume that f and g have no common root, then all the gamma is are distinct, right?
They have to be.
Okay. Yes. Okay. That's true. True. Yes.
Right.
True.
So now once the gamma is a distinct, this proof follows through because at every gamma I, both f and g cannot be 0. So at least one out of f and g has to have a sign, and the other has to be either like so at the first point, one out of f and g has to be positive, and the other one can be at most 0.
I see.
So its convex combination has to be positive.
Okay. Yeah. Strict convex combination.
And then same for the next one. At least one of them has to be negative. Because they both can't be 0, then that's a common root.
I think that's fine. Yeah. Yes. So we just have to take out the shared roots. Yes. So let me try to write it down. Well, then you have to say how you put the shared roots back in.
So I assume that f and g have no shared roots.
Right.
Right. And if they have shared roots, then we just divide them.
Well, you divide them, but when you put them back in, you have to say what you do then.
No, I just need to prove that f and g, all linear combinations of f and g are interlacing, right?
Are real rooted. Real rooted. So you factor out, then you add them, it's still real rooted. Yes. So there was one additional claim which we used later, which was that the convex combination is still consistent with the same interlacing points, which was useful which was important, although there might be other ways to prove it, but I used it to argue about the maximum root, which was important. But I think, yeah, let's forget that point. I think you have a nice solution. So remove shared roots. Then these must be distinct points. Because if not, then two of these roots would have to be interval of length 0, so they would be the same root. That's good. And then your next claim was that it's not possible that both f and g are 0.
At a gamma I.
One of f g must be 0 h gamma I, and that was because it would be a shared root, right?
Is it obvious, by the way, when
so
they still
the signs of h dx alternate.
Well, yes, because
as they should.
Because you remove one structure from each of the sides.
Okay, thank you. That's nice. Yeah. So I think we can stop here. Yeah. Thank you.
Grade 45?
Everything is indices get reduced by